Now that we can draw Lewis structures of compounds, we can combine those with valence shell electron pair repulsion theory to predict the three-dimensional shapes of molecules. So you can see this VSEPR, which we sometimes say as VESPR for short, is valence shell electron pair repulsion theory. So we use the theory that electrons, either lone pairs or bonding pairs, are going to repel each other. So just like if you put the parts of the magnets that are not attracted to each other and you try to put them together, they repel each other. You can kind of think of electrons as being that. They want to get as far away from each other as they possibly can. And so knowing that they want to get as far away from each other as they can, then you can predict the three-dimensional shape. So we're just going to go through some different examples, and if you have that chapter 8-9 handout printed out, you can have that in front of you. Or if you don't have a printer, you can have it pulled up on a screen just to show all the different shapes. All right, so we are going to start with steric number 2. So just a few designations. Here you'll see SN, or steric number, and that's the number of electron groups around a central element. So an electron group is going to be defined as either a lone pair or a bonding pair. And in this case, it could be a single bond, a double bond, or a triple bond, and those will all count as a single group. So even though a triple bond is 3 bonds or a total of 6 electrons, it is going to be physically restricted in space. So it still just counts as one group. All right, so we are going to start out with steric number 2, and in this class we are going to go up to steric number 6. So we're just going to walk through examples of all of them. So if you're going to predict the three-dimensional shape, you want to start with a Lewis structure. So we do that the same way as we've been doing. So you take carbon and see how many valence electrons you have, and it's 4. Oxygen has 6, and we have 2 of them. So a total of 16 valence electrons, and we have already drawn carbon dioxide. So I'm going to go ahead and just draw our Lewis structure that we've done before. So then you want to take a peek. The way you figure out the steric number, because I'm not always going to tell it to you, is you take a look at this central element and you say how many electron groups are around that central element. And so here we have 1, 2. So that's 2 electron groups. Then the next thing you want to figure out how many are bonding groups and how many are lone pair groups. So 2 of the groups are bonding, and we have 0 lone pairs. And this is the process we're going to go through for every single one to figure out the shape. So steric number 2. So if you take a look at carbon dioxide, these things want to get as far away from each other as they possibly can. So you wouldn't see something like this, because here these guys are really close and then these ones are really far away. So you really do want this situation where they're as far away from each other as they can possibly be. So then we have 180 degrees here. And the name of this is linear. So if I ask you what's the shape of carbon dioxide, you would draw the Lewis structure, figure out that it had 2 electron groups around it, so the steric number's 2. They're both bonding, no lone pairs. So they're going to get as far away from each other as possible, and you're going to have an overall linear conformation. So now let's move on to steric number 3. So we're going to use this as our example. Let's take a look at boron on the periodic table. Boron is over here, so it has 1, 2, 3 valence electrons. So 2 in the S's and 1 in the P. So 3. Each hydrogen has 1 valence electron. We have 3 of those. So 3 plus 3 is 6. Then we're going to put the boron in the middle, hydrogens around it, 2, 4, 6. So the way that we've drawn this, you can see, if you were looking at bond angles, it would look like this was a 90-degree bond angle, this would be 90 degrees, and this would be 180. But really, these 3 electron groups want to get as far away from each other as they possibly can. So if you have a model kit or even like some toothpicks and something you can stick the toothpicks on, like Play-Doh or whatever, it might be a good idea to have that out in front of you so that you can see these 3-dimensionally. I'm also going to post a link with some simulations, or you can take a look at fet.colorado.edu has some great simulations so you can kind of explore what this looks like 3-dimensionally. So the way this is actually going to look is more like this. And then what's the bond angle here? 120. All right, so then we want to ask the same questions. How many electron groups are there? There are 3 electron groups. And then we want to say how many are bonding and how many are lone pairs. So 1, 2, 3. 3 of them are bonding. And we have 0 lone pairs. So this lone pair thing is going to be more important as we go on. So then we want to say, what's the shape of this? So let's just pretend we're in preschool and I want to ask you kind of, what's this shape? So it looks like a triangle. And it's all in one plane. So if you turned it sideways, it would be all in one plane. So this one is called trigonal planar. And if you're following along with that table in the handout or in your book, you'll see that we have a trigonal planar shape here. So I'll just show you the table that we're looking at right here. So we have steric number 3, trigonal planar. We have 3 bonded atoms, 0 lone pairs, so it's trigonal planar. It looks like this. The bond angles are 120 degrees. All right, and BH3 here is one that's not following the octet rule. Okay, now let's take a look at another example. Okay, so let's find germanium. It is right here. So you can see it's 2 into the P's. So it has 1, 2, 3, 4 valence electrons. Each fluorine has 7, and we have 2 of them. So we have a total of 18 valence electrons. So we put the germanium in the middle, then we bond it to the fluorines. So that's 2, 4, 6, 8, 10, 12, 14, 16, and then 18. And again, germanium here is one that's not following the octet rule. You can see it, it only has 6 electrons around it here. So this is an exception to the octet rule. So now we're going to go ahead and ask the question about germanium. How many electron groups are around germanium? We have 1, 2, 3. How many of them are bonding? This one and this one. And then we have our 1 lone pair. So in this case, we still have 3 things around it. So this lone pair is this invisible force. Even though there's not a bonding pair there, there's this invisible force which is going to be pushing these guys down, right? So this is all negative charge, pushing them down. So now we have a case where we have an electronic geometry. So it still has 3 things around it. So the electronic geometry is still trigonal planar, like the last one. But the actual shape, the molecular geometry, is over here. So if we have 2 bonded atoms and 1 lone pair, then we have bent. So that lone pair is up here still forcing these guys down, but you can't see it. So the overall shape is bent. So I will want you to be able to identify both the electronic geometry and the molecular geometry for any compound going forward. Now we're going to move on to steric number 4. So there are going to be more and more possible shapes for every steric number that we go up. So the first one we're going to look at here is methane. And for some of these, I'm not going to go through the entire process of drawing the Lewis structure, just to save a little time. So carbon has 4, each hydrogen has 1, so a total of 8. All right, so here we have methane. And this is where it's going to be really important that you have like some toothpicks or some 3-dimensional object so you can see what this really looks like. Because if it were flat in this plane, it would look like these were all 90-degree angles here. But again, this is going to be in 3-dimensional shape. So here's what CH4 is actually going to look like. So it's not just a square. You can see if it's in 3-dimensional space, that if you're attaching 4 things and you want them as far away from each other as they can possibly be, that it's going to look like this. And the bond angles you can see are about 109.5 degrees. And the shape of this is called tetrahedral. So both the molecular geometry and the electron geometry is called tetrahedral. So we have 4 electron groups, 4 are bonding, and 0 are lone pairs. So the molecular shape or molecular geometry is tetrahedral. And the electronic shape is also tetrahedral. Okay, so steric number 4 with 4 bonding and 0 lone pairs is going to be tetrahedral. Okay, so still with steric number 4, let's look at ammonia. So for ammonia, remember nitrogen has 5 valence electrons, each hydrogen has 1. So that's a total of 8 valence electrons. All right, 2, 4, 6, 8. So each hydrogen is following the duet rule, nitrogen is following the octet rule. So now we want to count up the electron groups. We have 4 electron groups, meaning steric number 4, because those electron groups refer to the steric number. Now we want to see how many of them are bonding. 3. And then how many of them are lone pairs? We just have 1 lone pair. So now we're going to name this. The electronic shape is still tetrahedral. But now let's take a look at the molecular shape. So the molecular shape here, again, this is going to look like a triangle, but it's going to be like a pyramid. So it's trigonal pyramidal. So electronic shape, tetrahedral, molecular shape, trigonal pyramidal. So if you're working out problems and it just says, find the shape of NH3, the shape implies molecular shape. So if it's asking just for shape, then you would say trigonal pyramidal. If it's asking for electronic shape or both of them, then you would definitely need to solve for both of those. So here's a look at ammonia, and you can see this guy up here, that's your lone pair. So it still has that tetrahedral shape, the electronic geometry. And if you, let's see if I don't show those lone pairs, so it's still this invisible force, but if you look at it from this direction, it looks like a triangle. But then you flip it up this way and it looks like a pyramid because they're not exactly in one plane. It looks a little bit like a pyramid. So this is your trigonal pyramidal. So still steric number 4 with 1 lone pair is trigonal pyramidal. All right, now we are going to look at another example with steric number 4, and that is water. So we have already drawn the Lewis structure for water. So let's take a look here and count up our numbers. So we have 4 electron groups, still in that steric number 4. Then we want to see how many are bonding, 2 bonding, and how many are lone pairs, 2. So then our electronic geometry is still tetrahedral. And the molecular geometry or molecular shape is, and you can take a look at your paper, this is going to be bent. So let's see if we can find water. So again, the electronic shape is going to be tetrahedral. So if we show those lone pairs, they're still going to be here. So those like your invisible force pushing down on the other ones. Then if we get rid of them, you can see the molecular geometry is bent. So get in there and play with this model to really get a feel for it. All right, so I also want to take a second just to show you how you might see these drawn, or if you go on to take an organic chemistry class. So the first one we started with for steric number 4 was methane. So you can write it like this, but as we know, it's tetrahedral. It's not this square shape here. So normally the way you would write it something like this. So these two would be like this, but then one of them would be coming out at the board at you. So that would be drawn with this wedge here. And then one of them would be going back in the board. So you do these dash lines. And this kind of represents what's coming at you and what's going back. And then these are all 109.5. So that's a little bit more of a three-dimensional drawing of what something that's tetrahedral will look. And again, if you take a look at your handout here, you'll see this tetrahedral drawing here. So these are all of our steric number 4. This one has 0 lone pairs, and then if you have 1 lone pair, it's trigonopyramidal or pyramidal. And then if you have 2 lone pairs for steric number 4, then you have a bent shape. Now let's take a look at steric number 5. All right, so the first example we're going to do for steric number 5 is PCl5. Now you're going to notice for these higher steric numbers that we are going to be typically dealing with an expanded octet, because if you're going to be bonding 5 things, 5 electron groups is at least 10 electrons. So let's take a look here. So phosphorus has 5 valence electrons. Each chlorine has 7. So we have a total of 40 valence electrons. So I'm going to go ahead and just draw this the way that it would be drawn, the way that I showed you, with those wedges and dashes. And then we have lone pairs on all these chlorines. All right, so this is what PCl5 looks like. So again, we're going to ask ourselves those same questions. We have 5 electron groups. 5 of them are bonding. And how many lone pairs do we have? 0 lone pairs. All right, so now let's take a look at what this shape looks like. So here's PCl5. So if you look at it straight this way, what kind of shape? So you're in preschool, what shape is this? This is a triangle. And then it turns out this side looks like a pyramid. So you have a triangle pyramid on the top and a triangle pyramid on the bottom. So this is called trigonal bipyramidal because you have 2 triangle pyramids. Now let's take a look at these bond angles. So from here to here we have a 90-degree bond angle. And then if we look at this direction, these are 120-degree bond angles. So this is the farthest apart that we can get any 5 elements from each other. All right, so in this case, electron geometry is trigonal bipyramidal, and the molecular shape or molecular geometry is also trigonal bipyramidal. All right, so that's our first one with steric number 5. Now we're going to look at another one, SF4. So again, the first step is always drawing out your Lewis structure. So sulfur has 6 valence electrons. Each fluorine has 7. 28 plus 6 is 34 valence electrons. And you don't have to be able to draw these out with the angles and the wedges, but I just want to show you because it kind of gives you a better feeling. So again here, sulfur is having an expanded octet. And again, we want to ask ourselves the questions about electron groups. So we have 5 electron groups around sulfur. So again, keep in mind that you're just counting around the central atom. You're not looking at the fluorines, you're just looking at the central atom, the sulfur. So it has 1, 2, 3, 4, 5. And this counts as just, you know, one line and one line. So how many of these are bonding? We have 4 bonding. And let's check out those lone and 1 lone pair. So then you can take a look at your shapes. So the electronic shape is the same as the last one, trigonal bipyramidal. And the molecular shape, or molecular geometry, those can be used interchangeably, is what we call seesaw. All right, so here's what SF4 looks like, and here's the lone pair, and I just want to show that to you. So first we have the trigonal bipyramidal shape. And we want to remove one of these guys from the equator because we want to get rid of some of those 90-90 interactions. So we're going to get rid of this lone pair, or it's invisible. And then you can see here now it looks like a seesaw, right? See if I can make it seesaw. So here's your 2 legs, and then it's kind of seesaw, seesaw, right? So that's your seesaw shape. Alrighty, now we are going to move on to the next shape, still with steric number 5. Here we have ClF3. So each chlorine has 7 valence electrons. Each fluorine has 7 valence electrons. All right, and in this case, chlorine's going to be in the middle, and then you're going to put the fluorines around it. And then it's the central atom, the chlorine, is going to have 2. And so since it has 2 lone pairs, you can kind of represent it like this. So even though that little wedge is not a bond, I'm just showing that the lone pairs are coming off in different directions. All right, so now we want to ask the same questions. We have 5 electron groups around the chlorine. And how many of them are bonding? 1, 2, 3. So 3 bonding groups. And then let's count up our lone pairs. We have this one and this one. So 2 lone pairs. So that electronic shape is still trigonal bipyramidal. And let's take a look at what our new shape looks like. So this electronic shape, you can see these 2 lone pairs. These little alien heads are our lone pairs. And so we took those off. If we don't show those, what is the overall shape? It looks like a T, right? So this one is called T-shaped. So the overall shape here is T-shaped. All right, so we have one last shape for our steric number 5. And it's an I3-. So each iodine has 7 valence electrons. And then remember that -1 means we have an extra electron. So we have 22 valence electrons. So we're going to go ahead and put these iodines all next to each other. And then remember the electronic shape is still that trigonal bipyramidal. So I'm going to put a lone pair here. So one lone pair is coming out of the board at us, one is going back into the board, and then one is coming straight out. And we kind of just draw these lines. Remember, these are not bonding electrons, but it's just showing where those lone pairs are located. So now you can see if we remove all of these, then we're left with a linear molecule. And I'll go ahead and add these lone pairs so you can see where they are. All right, and now we are going to count the same things that we've been counting. So again, remember, we're just looking at the central atom when we're counting up the electrons around it. So we have 5 total electron groups. Steric number equals 5. And then we want to see how many are bonding. 2 bonding. And how many lone pairs do we have? 3. All right, and in this case, the electronic shape is, again, since our steric number is 5, because this is a 5, it's still trigonal bipyramidal. And our molecular shape is going to be linear. So you can see with our I3-, we have these 3 valence electron pairs. And then if we don't show those, you can see that overall geometry looks linear. So again, the electronic shape is trigonal bipyramidal, if you have those. And the overall molecular geometry is linear. We are now going to work on steric number 6. So the first one we're going to do is SF6. So again, like we always do, we start with a valid Lewis structure. So find the valence electrons for each. Sulfur has 6 valence electrons. Each fluorine has 7. All right, so this equals 48 valence electrons. And again, we are going to be dealing with expanded octets here. All right, and then we can put the lone pairs all over the fluorines. So then we count how many electron groups are around the sulfur. We have 6 electron groups. And how many of them are bonding? We have 6 bonding and 0 lone pair. So let's take a look at this. So this looks like an octahedron. So we have 90-degree bond angles all around. So this guy is called octahedral. You might also hear square bipyramidal because you can see that if we put it like this, then we look like we have a square. And then if we stand it up, there's a pyramid on the top and a pyramid on the bottom. So it looks like square bipyramidal or octahedral. So that electronic geometry is going to be octahedral. And the molecular geometry is also octahedral. Now we're going to take a look at another steric number 6. So first, you draw your Lewis structure. Bromine has 7 valence electrons. Fluorine has 7 valence electrons times 5. So a total of 42 valence electrons. All right, and then we have our one lone pair. So again, we're going to ask the same questions. How many electron groups are around the bromine? We have 6 electron groups. And then we want to see how many of them are bonding. 5 of them are bonding. And then we have our one lone pair. So if we're going to ask the same question about electronic geometry and molecular geometry. So we still have those 6 electron groups, so we know that this guy is still going to be octahedral. But let's take a look at what the overall shape is going to be. Okay, so for our BRF5, we still have that octahedral shape. But you can see when that lone pair is just an invisible force, if we don't show that, you can see that it just looks like a square pyramid. So it is called square pyramidal. All right, and then we are just going to look at one more shape. This is going to be our last shape. So there are other geometries, but we are just looking at this last one. So xenon is one of our noble gases, which typically doesn't, we say noble gases don't bond, but there are some exceptions. So xenon has 8 valence electrons. Each fluorine has 4, 4 times 7. So we get a total of 36 valence electrons. Or lone pairs. And again, you don't have to draw it like this. You could just draw like this, but I'm just showing you the wedges and the dashes, how you would see it drawn. So either of these is fine. All right, now let's ask ourselves these exact same questions. How many electron groups are around the xenon? We have 6 electron groups. Then let's see how many of those groups are bonding. 1, 2, 3, 4. And then how many lone pairs? 1, 2. All right, so since we have 6 electron groups, that means that electron geometry is still octahedral. And then let's take a look and see what shape it looks like if we take 2 things away from there. Okay, so you can see the electron geometry here for xenon tetrafluoride is still this octahedral shape. And then the overall shape of the compound, you can see it looks like a square. And it's all in one plane, right? Meaning it's like flat piece of paper. So it's all in one plane. So this is called square planar. Square planar is the overall shape. All right, so again, there are some other geometries with octahedral electron geometry, but we are not going to discuss them. So that is the completion of all the shapes that we are going to talk about in this class. So again, you can always refer to this. You just count up the, after you draw your Lewis structure, you count around that central atom to see how many electron groups there are. And then you figure out how many of them are bonded and how many of them are lone pairs. And this is going to guide you through and tell you what the shape is going to be. So keep this in front of you while you're doing them so you can figure these problems out. All right, so now we are going to do a few practice problems because so far, I was telling you exactly what shape we were going for. So now we're going to do some where you don't know the shape ahead of time. So let's practice some problems. All right, so here's what a question might look like that you might see on a test or a quiz. Predict the shape of ClNO, where N is the central atom. So the first step, if you're going to predict shape, and if it's asking for the shape, that usually means it's looking for the molecular geometry. So the first step you want to do is draw a Lewis structure. So we're going to take each of these. Chlorine has 7 valence electrons, nitrogen has 5, oxygen has 6. Then you're going to add all those up and say that you have 18 valence electrons. Then again, it told you that N goes in the middle. So then you're going to go 2, 4, 6, 8, 10, 12, 14, 16, 18. All right, so if we take a look at that, this doesn't look like a great Lewis structure because these ones over here are following the octet rule. This one is not. So we're going to need to go ahead and make a double bond. So we're going to want to move these ones in. So again, we don't want to put a double bond on chlorine because it's a halogen, so that's typically not going to double bond if it can't get away with it. So we're going to do the oxygen. And if you went through and did the formal charges of each of these, you would figure out that this is the better one to double bond. Okay, so you can go ahead and calculate the formal charges for these to convince yourself that that's our best Lewis structure. So now everybody's following the octet rule. So now we want to do the same procedure that we were doing before, where we're going to count up electron groups. So again, you're going to want to look at the central atom when you're trying to figure out the shape. So you look around there and see that you have 3 electron groups. Then we want to know how many of those are bonding groups. Now you might be thinking to yourself, but that's a double bond. Doesn't that count as two? And the answer is no. It's restricted in space, so it just counts as one repulsive group. Remember, we're doing VSEPR theory, valence shell electron pair repulsion. So this just counts as one group that's doing the repulsion. Now we want to see how many lone pairs, and we have one lone pair. All right, now you can go ahead and take a look at this guy. So we had a steric number of 3, so we're going to be up here. We had 2 bonded and 1 lone pair. So we know the electron pair geometry is trigonoplanar, and the overall molecular geometry is bent. So again, that electron geometry, because we have 3 things around it, is trigonoplanar. And the overall geometry is bent. And this is the answer that we were interested in. And let's take a look at another practice problem. We want to predict the geometry of BrO2-. So again, you always want to start with that valid Lewis structure. So you count up the total number of valence electrons. Bromine has 7 valence electrons. Each oxygen has 6. And here we're dealing with a polyatomic ion, so that negative charge means 1 electron. So if we add these all up, we get 20 electrons total, 20 valence electrons that we can put around. So again, that bromine is going to go in the middle, and then you'll have oxygens on either side. Now we need to distribute our 20 valence electrons. So we already have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So everyone's following the octet rule. It looks good. Keep in mind for those ions, we have to put it in brackets and put the charge. All right, so now we're going to ask those same questions that we were asking. And again, we're just looking right around that central element. So how many total electron groups do you see? 4 electron groups. How many of them are bonding? 2 bonding. And we have 2 lone pair. Okay, so what's the electronic geometry for steric number 4? That is going to be tetrahedral. And what's the molecular geometry for steric number 4 with 2 bonding and 2 lone pairs? It's going to be bent. So if the question asks you to predict the geometry of BrO2-, that means the molecular geometry. So the answer is bent. All right, so now that you know how to draw Lewis structures, how to use VSEPR theory to predict 3-dimensional shape, I want you to go ahead and work on some practice problems. So this is also on your handout. I want you to go ahead and hit the pause button and see if you can work all of these out. And I want you to predict both the electronic and molecular shapes of the following. Okay, so pause and come back. All right, so for BEF2, hopefully you got this for your Lewis structure. And you saw that it was linear. So both the electronic and molecular shape of this is linear. For number 2, you get steric number 4. So both the electronic and molecular shapes are tetrahedral. And the lone pairs aren't drawn on the fluorines here, but just assume that they're there. All right, so for number 3, you have 2 bonding and 2 lone pairs. So the steric number is 4, giving us an electrical shape of tetrahedral, and then the overall shape is bent. For number 4, PCl3, hopefully your Lewis structure looked like this. Again, we have steric number 4 with 1 lone pair. So the electronic geometry was tetrahedral, and the overall shape is trigonal pyramidal. All right, so now you know all about VSEPR theory, so go ahead and practice some more. Keep practicing drawing Lewis structures and predicting that 3-dimensional shape. And remember, predicting that 3-dimensional shape helps us figure out how molecules are going to interact with each other. So now we're going to further our knowledge. After we predict the shape, we'll be able to predict some different properties for our compounds.